All right. Hello, everybody. Welcome to this webinar. Thank you for joining us at 10 in the morning on a wonderful Saturday. Today's Green Energy Series talk is going to be about inverters and battery choices. This topic is very interesting, but there's certainly some nuances to this topic, and therefore we're going to do some deep dive into the inverter and the battery choices. This is going to be a recorded webinar, and it will be on the Solar Oregon YouTube channel shortly after this presentation. So Solar Oregon is a nonprofit. We've been around for around 36, perhaps even a few more years than that, years in Oregon. The nonprofit does education outreach to help Oregonians and folks in the Pacific Northwest go solar. We also offer solar tours and solar webinars and solar campaigns. Here's in the picture on the right is a solar winery tour, and we visited the agrivoltaics site that Oregon State University managed. Being a nonprofit, we would certainly appreciate if you could donate to our cause. There is a link to donate. And feel free to use the Q&A buttons to ask questions. I imagine this webinar will result in lots of great questions, and I'm happy to answer them. And so about me, my name is Edward Louie. I work at Pacific Northwest National Laboratory as a building energy efficiency research engineer. At Solar Oregon, I'm also on the board. And outside of work and also my duties at Solar Oregon, I'm working on building an off-grid zero energy tiny house as one of my main hobbies. And a disclaimer, this presentation, I've done my due diligence to present information accurately, but it does not necessarily reflect the position of Pacific Northwest National Lab, the U.S. Department of Energy, or Solar Oregon. And so with that, we'll kind of jump into the overview of this presentation. We'll look at inverter choices, battery choices, and then when you add batteries to the system, there are some nuances on how to operate a system with batteries. It opens the door to several more variables, and we'll talk about that. And then we'll look at the bill of materials in terms of cost of these different permutations of batteries and battery-less system and different types of batteries. And then we'll look at some comparisons, and then we'll conclude with some concluding remarks. And so in the world of solar inverters, you have a few choices. You have string inverters, and string inverters come in a number of flavors. You have perhaps the lowest cost string inverters are ones that just convert the DC energy from the solar panels to AC energy, and they have no capability of being able to be compatible with batteries. And then there are also string inverters that are compatible with AC coupled batteries, and then there are string inverters that are compatible with high voltage DC batteries. And then there are also string inverters that are compatible with low voltage DC batteries. And so those are kind of the landscape of string inverters. And then there's also the choice of microinverters. These are inverters that are much smaller than a traditional string inverter, and they live behind each solar panel. So the energy from the DC energy from the solar panel is converted by these microinverters, and so the energy coming off of the roof is AC electricity instead of DC electricity. And so we'll look at the pros and cons of each a little bit more in next slides. And so as I alluded to you, there are several battery choices. There are AC coupled batteries. The most perhaps famous and well-known AC coupled battery is the Tesla Powerwall. There are also high voltage DC coupled batteries. Perhaps the most well-known of these batteries is one made by LG Chem. And high voltage, in terms of high voltage, what does high voltage DC mean? We're talking about voltages that are in the upper 300s to below 500 volts. So typically around like 380 to 430 volts, somewhere in that range is high voltage. And then low voltage DC batteries are batteries that operate in the 12 to 48 volt range, with solar system typically using a 48 volt low voltage DC system. And there are hundreds of these different types of low voltage DC coupled batteries. I'm just showing some pictures of one example of many hundreds to choose from. And so, as I alluded to, operating with a solar with battery system results in a number of choices that are now that a number of variables and choices that are now available. And so one is an option on how to charge the battery. You can choose to have the batteries be charged from solar only, or you can choose to have it not only charged from the solar panels, but also draw energy from the grid to charge. And when you draw energy from the grid, you can specify what hours to supplement the batteries with the grid energy, and also at what state of charge to begin charging or to stop charging from the grid. To the picture to the right is one of these sliders or choices that you can make in the case of the Tesla Powerwall on making this choice. And in the case of the Tesla Powerwall, these choices are made using an app on your phone. For other types of batteries, the choices are, if they're not made on the app on the phone, it is made in the menu screen of the battery. And then at other times, it is made in the cloud by connecting the battery to the internet and then logging in through a web portal. So these are the kind of different ways that batteries allow you to go through the menu system to make these choices. And so why would anybody want to not just charge their battery from solar, but also charge their battery from the grid? Well, one reason for that is if you subscribe to a time of use rate for your electricity. And so by specifying what time and what state of charge to charge at and discharge at, you can utilize the lower rates in the off-peak hours of the day on a time of use rate. And so let's say in the wintertime, there's not a lot of sun, and so your battery is not able to be, that fully charged to be able to cover the on-peak hours of energy usage. So what you can do is specify that, okay, well, I need at least 50%, let's just say, for example, at least 50% of the battery to be full in order to make it through the on-peak hours of the day. But because it's winter and it's extremely cloudy, I'm not able to charge the battery to 50%. And so then you can program the battery to also supplement and buy and charge with some electricity from the grid during the off-peak hours, so that the battery is at 50% before the start of the on-peak period. And so these are just some examples how to program and set up a battery to allow the battery to do the most good for you. And another option is when to even use the battery. You can choose to have the battery only be exercised or used when the grid goes out. And so then, therefore, you would set it up as a backup only system. You can also set up the battery to be self-consumption only, meaning that the battery will never export a single kilowatt hour to the grid. And so the battery would only be used to provide energy at night for self-consumption. But you can also set the battery up to sell back to the grid at specific times and at specific amounts. And so in the right-hand picture, there's an example of, in the Tesla app, for example, a way to set up how much to sell back to the grid and also when to sell. in this case, the time-based control to sell back to the grid. And so going back to the time of use rates, there are utilities that not only charge you higher rates during the on-peak hours, but if you were to sell energy back to the grid, you get more dollars for your kilowatt hour if you sell back to the grid between in their on-peak hour periods, in this case, 5 to 9. This time of use rate comes from Portland General Electric. I'm not 100% sure that Portland General Electric will pay you more for your kilowatt hour if you sold it back to the grid during on-peak hours. I believe they do not. I think net metering is a separate thing from time of use.
I think you're right, Edward. I think it's just 1 for 1 at the base rate.
Yeah, exactly. So, but there are utilities that have different cell rates that are also time of use dependent. So you can, if that is the case, you can program your battery to take advantage of that. And so those are the choices on how to operate your battery. Now let's look at the cost of a system in different configurations, ranging from no batteries to the different kind of batteries. And this is a system that I picked out. 5.5 kilowatt is a pretty typical system for a residential home. It's not excessively large. And then also in later slides, we'll also look at some scenarios where if you have an existing solar system that's about this size and you were to add batteries, then you can kind of see in the price breakdown how much that adding a battery to an existing solar system would cost. One of the lowest cost systems you can possibly get is to have a system where you install solar panels and you have a string inverter, and the string inverter is one that is one of the lowest costs available. It may not be able to be compatible with batteries, but as a result, the bill of materials on that inverter is less, and so your total system cost is really inexpensive. A system like this would not provide any electricity during a blackout, so that is a caveat. But if you are on net metering, hey, it's a cheap system that allows you to participate in net metering, and that's a really fantastic deal. In a previous presentation, I talked about the problems associated with net metering, why it's not exactly a great deal for the utility, and perhaps how the future of solar is such that net metering will eventually go away, and you will not be able to get retail 1-for-1 payback or credits for the energy you generate, especially in the summertime for use in the wintertime. And California is moving in that direction. Or there's no sign that Oregon is moving in that direction yet for net metering, but it is possible given the direction that other states are going. So that's something to keep in mind. But like you said, this in the overall scheme of solar systems, this is going to be the lowest cost. One of the things that this first system does not really work well is if you have a roof that gets partial shade, because what happens with solar panels is that when you get one or more solar panels in a string that is shaded, the shaded panels will really kill the output of the entire solar array. And the reason why is those shaded panels create a bottleneck that restricts the flow of electricity through the system. And so one of the ways, low cost ways you can mitigate a roof that can occasionally get partial shade is to install power optimizers behind each panel. And so what these power optimizers do is they talk to each other, and when it detects a panel as being in partial shade, what it'll do is it will adjust the ratio of voltage versus the amperage to prevent the bottleneck of energy flowing through the system, and so that it allows the system to still produce a lot of energy even in a partial shade situation. But as you can see, this adds a little bit of cost to the system. It bumps up the dollar per watt from 0.7 to 0.8. So it adds a little bit marginal cost. Oftentimes what you'll hear is from solar panel installers is that they'll try to sell you microinverters. And the reason why they want to sell you microinverters is they'll say, well, in partial shade conditions, the microinverter systems are immune to the losses from partial shade conditions. And that is true because the microinverters work as they all sync to the same AC signal, which is from the grid. And when one is in partial shade, it will just generate less electricity, but they're not bottlenecking each other. But as you can see, microinverters are more expensive than a string inverter system generally. And they're even more expensive than a string inverter system with optimizers as part of the system. And so whether a system with power optimizers would be able to handle partial shade better or microinverters. Microinverters are slightly better in partial shade. They can still they'll produce a little bit more energy than even a system than a string inverter system with optimizers, but the difference is quite small actually. So another advantage of microinverters is if one microinverter were to fail, your system is still producing energy. But in the case of a string inverter system, if your main inverter fails, then you're not producing anything. So that's another reason why some installers want to sell you microinverters, but it does again come at a higher cost. Are microinverters likely to fail? Well, the first generation inverters that were made like 20 years ago, yeah, they had some failure rates, but that rate was still quite small, and those tests were done on inverters 20 years old. And modern inverters are even better built than inverters from 20 years ago, and so likely the failure rate of inverters is extremely small. So I don't know that is really something to be worried about. Okay, so we've kind of gone through the batteryless solar systems, and now we're looking at systems that include batteries. And one of the things that first comes to mind is, wow, when you add batteries to a system, you're quadrupling, quintupling the price of the system. Like, wow, that's really expensive. And it doesn't have to be always this expensive. We'll look at other scenarios where it's possible to add batteries to a system that doesn't cost as much. But this example, one of the things that to show is that if you add AC coupled batteries to a solar panel system, the system cost does go up dramatically. One of the takeaways from the slide is that AC coupled batteries is one of the most expensive choices in the grand scheme of battery choices. But one of the advantages of AC coupled batteries is that you can integrate AC coupled batteries to pretty much any solar system that existing solar system. You don't have to worry about whether it's compatible with the existing inverter or not. The reason why is AC coupled batteries, the reason why they're AC coupled is that batteries are inherently DC, and in order to get an AC coupled battery, the battery inside has a inverter also, and this inverter will be able to convert 120 volt, 240 volt electricity to the DC, and then also switch it around and be able to take the DC electricity from the battery and convert it to 120 and 240 volt AC. How Tesla does this and still allow you to operate your house during a blackout and not electrocute any linemen trying to restore power on the grid is they have something called a backup gateway, which is the little box, if you're able to see here, the smaller of the two wall hung pieces. And this contains electronics that can sense when the electricity on the grid is out during a blackout, and it'll automatically island the house, i.e. like disconnect the house from the grid. And then once this Tesla gateway confirms that the grid has been disconnected, then it will then signal the Tesla Powerwall to turn back on and therefore provide electricity to the grid without backfeeding the grid. And so it is necessary to have a gateway. In the wider scope of the technology, this unit is really called an automatic transfer switch, or an ATS. And we'll explore kind of what ATS, automatic transfer switch options, are out there that are not branded Tesla in future slides. But as you can see, that this gateway or automatic transfer switch is, not a small dollar line item in the whole bill of materials. And then another thing to note is that a Tesla Powerwall 2, which is the current generation of Powerwall, this is what, if you reached out to a Tesla, what's it called? Distributor, they will spec out a Powerwall 2 if you are trying to integrate into an existing solar system. But if you were to build a new system from scratch using Tesla solar equipment, they will actually spec out a Powerwall Plus. And the difference between the Powerwall Plus and the Powerwall 2 is that the Powerwall Plus has a solar inverter built in. And so as a result, then you don't need this separate solar inverter line in your bill of materials, because the solar panels can then connect to the Powerwall Plus directly. So that's something to keep in mind. In the world of AC coupled batteries, the market only has a handful of AC coupled battery brands to choose from. Tesla is the most famous one. There's some other ones that you may not have heard of, but I would say in the grand scheme of AC coupled battery, Tesla probably has like 75 or 80% of the market share. Okay, so and then also because it's AC coupled, you can also couple Tesla Powerwall batteries to a system with microinverters. And as we talked about before, just a solar system with no batteries, a microinverter system, is more expensive than a string inverter system. So you can imagine that a microinverter system with Tesla Powerwall is even more expensive than a Tesla Powerwall system with a string inverter. And we see that here, 28,000, and then you bump it up to 29,000 for a system that has microinverters and a Tesla Powerwall. And so, okay, so now let's look at high voltage DC coupled batteries. And so these batteries connect to the solar inverter. And so therefore, you need to have a solar inverter that is compatible with high voltage DC batteries. Luckily, there are quite a large number of inverters that are capable of interfacing with high voltage DC batteries. If your house came with solar and you're not sure what type of battery it's compatible with, I encourage you to look up the model number and then try to find the manual or specification sheet for that inverter. And there's a good chance that you will find, when you look at that specification sheet, that you'll discover that it is compatible with a certain brand of high voltage DC battery. And the world of high voltage DC battery, there's also only about a handful of brands to choose from, but the large number of inverters that are capable of interfacing with high voltage DC batteries, they have all made partnerships with this handful of high voltage DC battery brands to have at least one battery that is compatible. Because high voltage DC batteries do not have an inverter that converts AC to DC and DC back to AC, it has a smaller bill of materials. So logically, the battery would cost a little bit less. And do we see that to be true? Yes. The dollar per kilowatt hour for the battery in the Tesla Powerwall is about $852, and the high voltage DC battery is only $711. So yes, we see that reflected in the price of the batteries. By having a smaller bill of materials, they are a little bit less expensive. But one thing to note is that inverters that are compatible with high voltage DC batteries, they have some more hardware in there so that it can convert the solar electricity not only to AC, but also convert the solar electricity to high voltage DC to charge the battery, and then also be able to convert the high voltage DC energy back to AC at the inverter. So therefore, the inverters are a little bit more expensive. As you can see, this inverter is $1,049 versus a traditional just string inverter that's not compatible with batteries is only $749. So it's a few $100s more for an inverter that is compatible with high voltage DC batteries. That's generally the case, even if we don't look at this brand and look at another brand. And then in order to allow these systems to keep the lights on during a blackout, again, the system needs to have an automatic transfer switch in order to disconnect the house from the grid so that you're not backfeeding energy and potentially harming a person trying to restore power on the grid. In this case, this company makes a transfer switch that's less expensive, but we will go later into a slide that explains why it's less expensive and perhaps one of the cons or caveats on choosing a transfer switch that's less expensive. Okay, so now looking at a system with low voltage DC coupled batteries. So one of the things that we can see in this example is that the inverter costs a lot more than other inverters. So this inverter is $4,500 versus even an inverter that is compatible with high voltage DC battery that's only $1,050. So they cost a lot more, but okay, well, where is the savings then? Well, the savings comes from that low voltage DC batteries are much, much less expensive than batteries that are AC coupled or high voltage DC coupled batteries. And the reason why they're less expensive is because unlike the other two options where there's only a handful of brands and makes and models to choose from, low voltage DC batteries, there's hundreds of brands and each of them have a portfolio of batteries to choose from. So this market is very saturated with competition, and that brings down the cost of batteries. As you can see, the high voltage DC batteries are about $700 a kilowatt hour. And then let's go back and remind ourselves, AC coupled batteries, $850 a kilowatt hour. And low voltage DC is less than half that price at $300 a kilowatt hour. So much less expensive. And so you pay more for an inverter to be able to interface with low voltage DC batteries, but then you're able to then buy cheaper batteries and your total system cost actually comes to be less. And if you were to expand this system and buy more batteries, it is less expensive for you to buy more batteries down the road. Okay, so now let's kind of take a look at the system comparisons in a table. And as you can see, kind of where this line here, after the third row in the table, you break into batteries into the system. And as I'm saying, when you add batteries, it adds a lot of cost to the system because solar is extremely inexpensive. Batteries are certainly coming down in price, especially in the low voltage DC coupled battery arena. But because there's only a handful of choices in the high voltage DC and AC coupled battery choices, the prices are still fairly high. Now you do save some in terms of the inverter. So if you don't ever plan on having more batteries in the future and expanding out your battery options, it is conceivable that it is possible to build a system that is high voltage DC or AC coupled that may be a little bit less than a low voltage DC system. And what I mean by that is these systems examples are spec'd out with about 20 kilowatt hours of storage. 20 kilowatt hours of storage is about what you need for a typical house in order to get through the night, to be mostly, not independent or not dependent on energy from the grid. And then also, typically the longest blackouts you'll ever see are less than a day. And so a system that has about 20 kilowatt hours of storage is generally a good choice. But if you choose to have a system instead of having 2 Tesla Powerwalls and you have only one, then you'll certainly be less resilient and you won't necessarily make it throughout the night without using energy from the grid. But because you're grid tied, when the Powerwall runs out of energy, then the house will just automatically switch to using energy from the grid. So it's not a problem when the grid is available. And so if you were to use just one Powerwall or just one high voltage DC battery, then obviously the cost of the inverter, the high cost of the inverter in a low voltage DC setup could make these numbers look a little bit different. And so that's something to think about. And let's kind of look at one of the caveats that I mentioned about the high voltage DC system. So one of the things that is absolutely necessary in a system that with batteries, and you desire that system to continue to power your house during a blackout, is to ensure that the house does not send electricity back to the grid and potentially electrocute line workers that are trying to restore power. And so it's absolutely necessary to have a automatic transfer switch to disconnect the house and island the house so that the energy to power the house stays within the house during a blackout. And if you were to do that and be able to island the entire house, then you need a transfer switch that's capable of switching 200 amps, because that is the size of a main service panel, a main circuit breaker panel in your house. And the Tesla gateway is capable of doing that. And the inverter that is shown in the example for the low voltage DC battery setup, that one has also a 200 amp transfer switch built into that inverter. Whereas in this example, shown, the automatic transfer switch for the high voltage DC coupled battery example, that transfer switch is actually only capable of 48 amps, so therefore not sufficient to transfer the main circuit breaker panel in the house to be able to safely island. But 48 amps is more than enough to transfer a sub panel of critical loads to island. And so in order to use this transfer switch, you would need to figure out which circuits on the main panel are critical loads, have the electrician install a sub panel, and then move those circuits over to the sub panel in order to use this transfer switch. But the high voltage DC system, if you were to pay about $1,000 more, so $1,500, and a lot of the transfer switches that are capable of 200 amps cost more, and so these 200 amp capable transfer switches would allow you to have a high voltage DC battery that can be able to island the entire main circuit breaker of your house. So what I'm trying to say is that if you were to do a high voltage DC coupled battery system and you want to be able to back up your whole entire main circuit breaker panel on your house, you can just switch out this automatic transfer switch to one that is a little bit more expensive, closer to $1,800 or even $2,500, and you'll be able to back up the entire main circuit breaker panel of your house. So that's something to know about transfer switches and selecting transfer switches. Now, when we look at systems, and especially the ones with batteries, and their kind of eye-watering prices, being much more expensive than just pure solar systems with no batteries, you would think that they'll never pay for themselves, and that's maybe the case right now without any tax breaks or incentives. Like right now, if we assume, let's say, like the batteries last 20 years, and we calculate out how much energy that they'll generate throughout a year, and then divide that out and multiply that by 20 years, and then divide the first cost of the system, then we find that like the levelized cost of energy from a system that has AC coupled batteries and high voltage DC coupled batteries is more expensive than the current electric utility rates in at least Portland, Oregon. But my friends in California are paying 30 something cents a kilowatt hour for their electricity. So actually, a Tesla Powerwall or a high voltage DC coupled battery system would actually save them money, even before any tax credits or rebates. All these numbers here are before any tax credits or rebates. So there are places in the country where the cost of electricity is high enough that even AC coupled battery systems, which are the most expensive systems looked at in this example, would be cost effective without any tax credits and rebates. And then once you factor in tax credits and rebates, then these numbers fall by usually about 40%. And so, but one thing to point out is that systems that are using low voltage DC coupled batteries, even before any tax credits or rebates, here in Portland, Oregon, at least, is already below the cost of retail cost of electricity. So that's fantastic. And then also, before rebates and tax credits, another kind of metric to kind of think about is a metric of simple payback. And if you expect your batteries and your solar system to last 20 years, is the system going to pay back itself within the lifetime of the equipment? And if it's not, then maybe you might not do it. Ultimately, both levelized cost of energy and simple payback are metrics that may not really matter to you too, because what is the value of a house that is resilient to blackouts? And especially if you have equipment that's needs to remain running for life safety, or just resiliency from extreme heat or resiliency from extreme cold, to be able to run your heat pump or furnace during those periods. Those things are, and many people would say that that's priceless. And so take the levelized cost of energy and simple payback numbers with a grain of salt, and kind of really ask yourself, when you add batteries to your system, like, why are you doing it? Are you doing just purely for economic reasons, or are you doing it because of energy resiliency, or you're doing it because you care about the planet and carbon? Because at night right now, if you are using a solar system on net metering, at night you're using electricity from the grid, and the electricity from the grid has a certain amount of carbon associated with it, because it's not 100% hydro. It's certainly not 100% nuclear. And so, a fraction of that electricity comes from natural gas power plants, and that obviously has a carbon associated with it. And so if you add batteries, then you're running on solar electricity even at night, because you're storing solar energy during the day and using it at night. So that's something that's also not kind of reflected in levelized cost or simple payback metrics. Okay, so some conclusions we want to be able to make kind of from this slide deck is that one is, if you have an existing solar system, check to see if it is compatible with high voltage DC batteries. if it is, then if you add batteries, it's less expensive to add high voltage DC batteries to that compatible inverter than it is to add AC coupled batteries. But if it's not compatible with high voltage DC batteries, then your only option is to go with AC coupled batteries, which are more expensive. But there are, like I said in the previous slide, there are many reasons to do it still. But in a new system, adding AC coupled batteries is quite expensive. And so if you're going to build out a new system, perhaps consider a inverter that's compatible with low voltage DC batteries, because as we see in the examples, there are significant cost savings to doing so. And then whatever system you choose, look into what the cost is to have a 200 amp automatic transfer switch in the system, because being able to transfer your main circuit breaker over to being full house backup can be less expensive than the electrical labor cost to install a sub panel and then moving circuits over to that sub panel. So we think that the cost of the 200 amp automatic transfer switch is around $1,800. You could easily exceed $1,800 in labor and material costs to add that sub panel. So that's why, even though it sounds expensive, it's actually not. And then also it's to save in installation labor cost, selecting a system with fewer field assembled components is a good thing. An example is for example, this picture on the right hand side, if this system were to be installed in 2023, it's certainly not the most cost optimal system choice to make, but it might have been however many years this system was installed. So anyways, that's kind of that, and I'll open up to questions.
Thanks, Edward. There was just one question, and it's been answered about the acronym BOM. Could you talk a little bit more about, and I know it's easier to look at just what do the parts cost, but about installation costs?
Right. Yeah. So we're talking about installation labor costs. Labor cost, I would say, in a residential system, it costs about somewhere between 40 to 50% of the material cost. So it's not quite double, but it can be as much as double the cost of if you figure out your hardware cost and then times 2, that'll be a safe number. But if you don't times 2, you take do the 40% calculation. That's also kind of within that range. The thing that's to think about is tax credits and local incentives usually add up to be about 40% also. And so one way to also think about system cost after rebates and tax credits is that after rebates and tax credits, this is kind of what you're left with out of pocket. And then therefore you want to care about calculating stuff like simple payback periods and levelized cost, and you can take the material cost and use the material cost only to do those mathematics, because
that sounds reasonable. I like that trade-off between the credits and the labor. Marcia asks about what about panels supporting structure anchoring to the roof? Are you including that in your panel cost, the rack or whatever they're using up there?
Right. Okay. So so I'll highlight that in this note section here. So the system cost comparison that we're looking at is looking at only the components that vary across the scenarios. And so therefore we're not talking about racking and wires, which generally remain the same across the scenarios.
Yeah.
The cost of racking wires will add, let's just throw a number out there, $2,000 to residential system. That's a pretty safe number. But since it doesn't vary across any of these scenarios, we're not including that in the comparison.
Right, it's all about comparing. I know in my system, well, my 2008 system didn't involve any rafter reinforcement because the code was not there. And by 2019, when I added to the other side of my roof, so east west, then the code had changed, and that was about $3,000 of 2x4s or whatever they were using, of 2x6s to
engineering plus the cost of labor.
Right, the calculations for the engineering and then the labor and the materials for that.
Right.
Marcia's full of good questions. Let's see. Instead of a permanent battery, do you foresee a bi-directional vehicle to home? Oh, anticipating next month's topic, set of electronics by which an EV battery 20 to 100 kilowatt hours could be used when the EV is in the house when power. Yes, Marcia. Wait till you see what the next presentation is.
So our next presentation, May 6th, is going to be talking about vehicle to grid and vehicle to home, its current states, and what does the future hold for that feature. Will this ever be a replacement of stationary home batteries or not? We'll kind of dig into that in the next presentation.
Looking forward to that talk. Yes.
Okay. Other questions?
I think, well, that's what we've got in the Q&A, and the chat's been pretty quiet.
Carrie, have you also enabled people to unmute themselves?
I have not, and I think I have to do that one person at a time.
Oh, there's not a global unmute. Okay.
No, it's weird.
Okay.
But if anybody wants to be allowed to talk, you could send a message in the chat.
Yeah. And then we can also do a plug on not only the next presentation, we do a next presentation, which will talk about the batteries and fire code. And one of the things to kind of think about in this presentation is that the codes have changed. And I'll get into the politics of the code and whether it's justified or not. But because the codes have changed, a lot of the pictures you see online of battery systems installed don't meet the current code. And so there are things about current code that, when somebody installs your battery system, it will not look like a lot of pictures you see online. So that's kind of a little plug for this presentation in June.
That sounds great. I'm looking forward to all of it. Well,
okay.
If there aren't any other questions, everybody can get back to their regularly scheduled Saturday program. And thank you so much, Edward. And we hope you'll all join us next month. The recording for this will go out by an email to everyone that's registered. Oh, here's another question.
Oh,
you be the presenter for the next two? Yes. Edward will be our presenter for the next two.
Yep. And then well, we hope to send out the slide deck and then also an Excel spreadsheet of all the different tables. And so feel free to then use that spreadsheet to change the numbers or add a row, subtract a row, depending on your needs. But yeah, that'll be a resource for you to use.
Oh, that sounds great. Okay, I think that is all of the questions, and I think they've been answered, and some of, it's going to come next time. So thank you very much, and we'll see everybody next time, I hope. All right. Here we go.
Take care, everybody. Thank you. Bye-bye.